when I have vectors that look like this, these are the kind of things that you've been doing graphically. The airplane with the wind blowing against its course, or things like airplanes taking off, or roller coasters that travel along the horizontal and then go 15 degrees up from the horizon. And you can solve these graphically pretty easy. The problem is there are no right angles here. You can't use Pythagoras on these things. Gesundheit, no? Yeah, so we don't have right angles to work with, so what we kind of have to do is create them for ourselves. And we end up creating series of right triangles and then a large triangle. I'm going to tell you right now that color coding today is huge. If you want to stop and grab colored pencils, I would recommend it. We'll start off with the sample problem 3C on page 95 in your book. And what we're told, this is kind of a mappy question. We have a hiker who starts at some base camp. Because I have the ability to move this, I'm just going to put base camp kind of in the middle of my drawing. And she walks 25.5 kilometers at 35 south of east. So immediately, starting from my little base camp, I need to draw myself a miniature compass rose. And when we're doing non-perpendicular vectors, you're always going to draw yourself a compass rose every time you start a new component vector. So she's at 35 south of east. This, of course, is east, so we're going this direction. It's going to be a little bit less than 45. And the nice thing about these, if you have been feeling constrained by graphical construction, and I'm actually going to expand this. Oops, that's not right. If you've been feeling constrained by graphical construction because, actually let's do that the other direction, of the precision that's required and the degree to which you have to really be so careful, you'll like this, because you should reflect to some degree the scale, but you don't have to make it, you don't have to be nitpicky. Don't make a 25-kilometer line the same distance as a 10-kilometer line. That should be roughly half, but also you don't have to be terribly precise about it. So she starts off, that's day 1. I'm going to actually change colors for day 2, and you'll see why. On the second day, she walks 41 kilometers, 65 north of east. So I'm starting from here, I'm starting from my next point, and she's going 65 north of east. So that's a 60-degree angle, roughly. And this line is significantly longer than my first one. And we're going to say that this is 41.0 km. Make sure you label those angles. It really helps. So what we want to know, of course, always, is her resultant displacement, which is that. So the idea of making your own right triangles, in fact, is exactly what we're going to do. We will come up with a right triangle for each of these, because what's true is that for that overall displacement, and I'll do a dotted line for this. You can do dotted lines by changing the spacing on here. It's true that overall for that resultant displacement, there was a delta y resultant, and there was a delta x resultant for her displacement resultant. Okay. So our goal is actually to get that resultant right triangle. Well, before we can do that, we have to figure out her x displacement for that first leg, her y displacement for that first leg, her x displacement for the second leg, and her x displacement for the third leg. It's not as bad as it sounds. These problems are not complicated. They're just tedious. These problems reward good bookkeeping. This is, I mean, seriously, this is an accounting issue. This is keeping everything straight because none of the math is hard. So let's show those other triangles. Really important, and I didn't do it here, and I just talked with a student about that yesterday, to make sure you put heads on your vectors so you know which direction that vector is going. Because remember, sign is going to be a proxy for direction, and if you screw up your signs, you screw up your magnitude in a lot of cases. So there we have delta y1, delta x1. Oh, shoot. What did I do? How did I make that more complicated for myself? Where's my angle? Where's my angle on that first leg? It's right there. Is my angle inside my triangle? No. So, the finer points. Remember that vectors can always be moved parallel to themselves. This is also that. This is also that. Yes. Yeah, you're going to have to be very careful about sign. That's a little bit better. We get some of that out of there. You can do the other triangle. You just have to be really careful. And it's easiest to do triangles that use the angles you're given. Okay. So on the second piece, can you see the second triangle? Can you visualize it? Well, there she blows. Okay, so we've got our delta x2 and our delta y2 labeled. One of the compelling reasons for color coding this stuff and for doing good bookkeeping is just keeping your calculations together. So I tend to actually draw sort of boxes around my calculations that color code correspond to my triangles. And that helps me see where all the numbers go. Because you're going to have a lot of numbers on the page or on the screen or whatever. So let's start off with our first triangle. We're going to be using trig functions to get all of, let me see if I can shrink this slightly to give us a little bit more room to work. So here's the thing, we kind of started from the back on this in terms of showing that last triangle first. So let's continue that and say this. We know that the resultant vector is equal to the square root of delta x resultant squared plus delta y resultant squared. True? Now the goal is just to figure out delta x resultant and delta y resultant. For our first triangle, this 35 is directly across from the delta y. So we know that if we take the sine of theta, it's equal to what? So, opposite over hypotenuse, which in this case is going to be delta y1 over the 25.5 k And we can solve that and say that the sine of theta times 25.5 km will give us our delta y 1. Easy enough. And yet, theta is the 35. Good question. Yeah, when you're, and you know what, the other piece of notation you can use is doing theta sub 1 to remind yourself that this is the first angle. This is the angle in that first triangle.
I couldn't tell because in my drawing it looks like the line is cutting at 35.
Yeah, and this is where your drawings, you see why suddenly the drawings are even more important. If you screw up your drawing, you will very often lead yourself down a blind alley. You'll lead yourself down doing the calculations wrong because you're depending on the drawing to show how the things are relating. So you have to be meticulous about your drawings now. Okay, so we have what, 14.62 what? 619. What I typically do for myself when I'm solving these is I'll write at least like the first chunk, equals delta y1. And I just leave that in the calculator so that I can scroll back up and grab it because I'm not re-entering all those numbers. That's ridiculous. So I make a note of those, I make a list of that. Now, if we want to get delta x1, what trig function are we going to use? Cosine. So we know that cosine of theta 1 is equal to the opposite over the hypotenuse is equal to delta x1 over our 25.5 km. Now oh gosh, yes, it is adjacent. Thank you, ma'am. And I'll draw my little bendy arrow so I remember that. Now, I'm starting off with the whole sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse. We won't do that forever. Once you're comfortable in doing these a lot, you're probably just going to hop straight to, okay, cosine theta 1 times 25.5 km equals delta x1. And that's fine. Once you're comfortable with that, once you've had some practice, when we start the projectile motion stuff, we are beyond ever doing that. Cosine equals adjacent over hypotenuse equals delta x over velocity. We're just going straight into cosine times velocity equals velocity on the x. Okay. So what do we have for a raw number?
20.88837713.
Okay. Km equals delta x1. And I tend to also circle or note because you're going to get a really complicated looking page for yourself. And if you thought it was important for me to follow your work when I'm grading, it's more important for you to follow your work when you're doing it. So marking these off, as I said, I not only color code, I tend to block off. Sometimes if I'm feeling especially stupid, I draw a line for myself to that triangle. Now, let's talk about sines, shall we? So, we've said that, we are programmed to a Cartesian coordinate system, positive, negative, negative, positive. Is that first y displacement positive or negative? Negative. Now, do you have to put in that it's negative? No. But you darn well better make sure that you realize that the y resultant is the difference between your two y's. You're adding them, but that y resultant is less than your second y resultant because they're working against one another. One's in one direction, one's in the other. The easiest way to do that is to assign signs early. There's nothing in that says it's negative. There are, I don't know any high school physics teachers who do it this way. I do know people who, rather than using that as 35 south of east, would say that that is, what, 90, 180, 270, whatever that angle is, coming all the way around the full circle. I find that worse. I tried it once, and the students found it worse too. So I've kind of stuck with, visualize it, have the picture, assign negatives where they're needed, use the actual angle you're given. Because that is the way it's given to you. Okay, so now for that next triangle, and I'm going to switch colors here. If we look at the angle, we know that y is right across from it, so we're going to use sine. So sine of theta 2 equals delta y2 over 41.0 km. Sine of theta 2 times 41.0 km equals delta y2. What do we have for a raw number? Okay, so we've got 37.1586, etc., etc., etc. You can't see my little ellipses very well there. Is our delta y2. Positive or negative? Positive. And that's where making sure you have heads on your vectors, making sure you have arrows on your vectors, really, really helps. To get our delta x2, of course we're using cosine, because it's adjacent to the angle. And we know that cosine of theta 2 is equal to delta x2 over 41.0 km. Cosine theta 2, times 41.0 km equals delta x2. Got a raw number? All on, yes, sir.
How do you go back and pull the numbers back out?
Let's do a quick tutorial on that. If you use the up button,
See how to go up to get it?
and then just hit enter, and it'll pop down to the new position.
And then how do I get the other one?
You'd like to add them?
Yeah.
So hit the plus button, go back up, select the number, hit enter, it'll pop down into position. Saves you a ton of work, and also I tend to miscopy numbers because my eyes do funny things. So I tend to miswrite my own number strings, and if I'm pulling them off the calculator, I save myself that problem. Okay, so I'm going to circle that for myself. I'm going to put this here. And now, wrong thing, Moser. And now it's time to start thinking about building our big triangle. I have had students in the past who have said, it's easier for me if I pull those triangles out. Sorry. And you can certainly do that. And sometimes I do, especially if it's a really complicated one. And I tend to use full sheets of paper. So I'll actually draw myself this little triangle on here with my 65, my 41, so that I can see it. I don't always. So let's look at, this is badly drawn, you'll understand that one, with our resultant. So we can deal with either one first. Force of habit, I always deal with the x first. Delta x resultant equals. And I tend to write this out, which I know may seem silly, but like I said, this is all about accounting. So delta x resultant equals delta x1 plus delta x2. I could do a better job with that. So delta n and delta x1 and delta x2 are both in the same direction. She's traveling east both days. So I'm just going to pull. Let's see, can I just get that? Well, I should have copied, not moved, but okay. Both in the same direction. What is my delta x resultant? Here's the other thing. Here's the thing that I forgot to say this. This is the thing that I do for myself, again, to prevent myself from doing dumb stuff. I tend to write over or next to the magnitudes. I tend to draw a little arrow that shows me which way it's moving. So, you know, I'll have that. In place, and that helps me remember, okay, these things are being added. Okay, so I've got my values in for delta y1 and delta y2. I've got arrows to remind myself which direction these things are moving. And I'm now ready to get a raw number. And yes, they are incredibly tedious. Pause. When you get to this point, I do suggest that you redraw that resultant triangle because it really is helpful, especially in finding the heading. Because remember, you also have to find the heading. So I'm actually going to copy all of this to the next page. Whoops. Wow, not that big. Okay. And I'm going to draw my resultant triangle. Oops. So you see how you can get that to be a solid or a, oh, it's not showing up on yours. Weird. Okay. So I now know that r equals the square root of delta x resultant squared plus delta y resultant squared. On your paper, on a test or something, I do expect you to write that formula, and I do expect you to write in the value that you got for delta x resultant and delta y resultant. We've got that. If you're using the multi-views, how many of you are comfortable with pulling a number up and squaring it and getting the square root? Any twitches? Okay. I feel like there should be a drum roll here. Are we all getting 44.3638, blah, 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 blah? Okay. Kilometers. Are we done? Of course not! We're never done. What do we have to do? Find the heading, yeah. So at this point, you know how I keep saying, like, don't rely on numbers that you calculated, don't rely on numbers you calculated? Guess what? You got no choice. You are so far into your own calculations that if you've made a mistake by here, you're just down the rabbit hole. But you'll be fine. But if you leave me a breadcrumb trail that I can follow, I can give you points for your trail. You know? So we're looking at this angle. We're going to use a tan function. Sorry. We're going to use a tangent function. So our opposite is our delta y resultant, and our adjacent is our delta x resultant. So the tangent of delta y resultant divided by delta x resultant is going to give us our theta resultant. And so if we take the inverse tangent, oh, I'm sorry, I did that backwards, didn't I? Yes, I did. Get your math function straight, Moser. There. Delta y resultant over delta x resultant equals the tangent of theta. So the inverse tangent of, whoops, no, don't cut it. Paste. Paste. Of that is going to give us our resultant theta. I would recommend strongly that on a test write in those numbers, you know. So write in that this is 22 point blah, 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 and this is 38 point blah, blah, blah. Because that way, again, I can follow your breadcrumb trail. If you've screwed something up, I can go back and trace. And I do. I mean, grading these tests especially takes a long time because I trace through all your work. These are tough and tough to grade. We all getting 30.524, etc. Good. Now, equals theta. What the heck did we write down as an answer? I don't know, because my brain's running out my left ear because I've just done an entire sheet of calculations. Your entire answer for this thing is as follows. Let me pull at least this part over to the next page where we've got room to work with it. All of that work gets you this. Resultant heading is, now how many sig figs do we have? 3? Okay. 44.4 kilometers at 30.5 degrees, and it's what heading? Let's grab this. What'd you say?
North of east.
North of east, yes. Okay. I didn't hear the of. Like, ah! Yeah, north of east. And that's, again, where having replicated this little triangle helps you because it means you can go, okay, yeah, that is north of east.
Where did you get your sig figs at?
Sig figs from all the way back in the beginning, from our givens. So 25.5 kilometers, 41.0 kilometers, whatever numbers were your givens that, Actually, you know what? I should be careful. Was that 65 and 35? Were our angles only 2?
Yes.
Oh, then you know what? We don't have 3 sig figs. Because your angles do figure in. Whoops. So that would be 44 kilometers at 31 degrees north of east. And your book very often gets the sig figs wrong. Oh, no, they did. They got it right in this case. They got it right. So, yeah, 44 kilometers at 31 north of east. Not so bad, right? They're not. They're really not bad. They're lengthy and they're tedious. And they reward good bookkeeping, good accounting, and, like, really careful organization of your stuff. So, okay. I'll have you get started on page 97, numbers 2, 3, and 4, and then I will get you the worksheet for this. Yes, sir? Yeah, though it's not going to be a... No, I didn't. I said one's not assigned. You want me to still draw the triangles for fun?
Not for one.
Okay. All right. 2, 3, and 4 on page 97. Yes. 2, 3, 4, page 97, and I will get you the worksheets.